Hello, welcome back to lecture 13 of this course on tectonics and geodynamics. So, we are now going to talk about, we've talked about how motion takes place on a spherical earth. So, we are now going to talk about calculating the linear velocity and finding out the direction of the velocity on a spherical earth based on what we are actually, based on the principles that we developed looking at a flat earth. So, let's just now skim through to what exactly we're going to, what kind of concepts we're going to cover in this particular lecture. So, the whole objective is, now we know that motion on the surface of a sphere, right, motion on the surface of the earth, for example, is equivalent to the motion on a surface of a sphere, and that is how we will try to treat it. So, what we will try to do is to find out what exactly would be the linear velocity at any point on the plate boundary. At any point on a plate boundary, what would be the linear velocity, what would be the direction, what would be its azimuth, right, in order to actually find out exactly what the type of motion is along a particular plate boundary on a spherical earth, because ultimately all plates are actually operating and moving with respect to each other on the surface of the earth, which is a sphere. So, let's now just recap into how we actually approach this whole problem. We thought about things in terms of a spherical earth. Now, on a spherical earth, the way in which we translated the concepts we developed on a flat earth onto the spherical earth is by using Euler's fixed point theorem, which we talked about in the last class. And if you remember, the statement of Euler's fixed point theorem is that the most general displacement of a rigid body with respect to a fixed point is equivalent to an axis passing through that fixed point. So, essentially what it means is that you can't have any kind of motion on the surface of the earth. You can actually treat that motion as a motion about an axis that passes through the center of the earth. Obviously, this axis has nothing to do with the rotation axis of the earth. It's an imaginary axis, right? It's the Euler axis of rotation, and this pierces the earth in two points. Now, these 2 points, just to recall, right, these 2 points, right, so once again, this is geographic north, this is geographic south. So, for any demarcating the motion of one particular plate on the with respect to another on a spherical earth, we can model it in terms of rotation axes, right, about an imaginary axis of rotation, which is called the Euler axis of rotation. This Euler axis of rotation passes through the center of the earth, and then it pierces the surface of the earth at 2 points. So, these, in this case, this would be 1 point, and that would be 180 degrees opposite to this on the other side of the earth. So, this, let us say, is a positive axis. So, this would be my rotation axis. Now, although this is the geographic north pole, you can see that if anything moves, if any object moves on the surface of the earth, it essentially can be modeled as a rotation about, it can be modeled as a rotation about this particular axis here. So, if it's a rotation about this particular axis, essentially every movement, any movement that it takes place, right, assuming that this is a positive one, right, any movement that takes place would take place along the arcs of small circles about this imaginary axis of rotation. So, every movement on the surface of the earth can be modeled then for that particular set of for that particular plate boundary, the motion of any point on that plate boundary, you can model it as the motion of as a rotation about on a small circle about that imaginary axis of rotation. Okay, so to specify this, if you remember, we need to specify what is the latitude and the longitude of the Euler axis of rotation, and we also need to specify the magnitude of that rotation, which we actually depict by the angular velocity about this particular axis. So, the location of the Euler pole of rotation, right, with respect to the geographic north and south poles must be specified by the latitude and the longitude of the Euler pole of rotation, right, and the magnitude of that rotation is actually depicted by the magnitude omega, which is the angular velocity. So, essentially then, just remember that any movement is a small movement about an Euler axis of rotation is essentially a movement on a small circle with respect to that axis of rotation, right. So, we have actually drawn in longitudes here just to show you what these longitudes are, but these do not have much meaning with respect to exactly what we are going to talk about in the context of they have nothing to do with actual longitudes except for specifying the position. Once again, just to continue with this, with the Euler axis of rotation, right? So in this case, this is the Euler axis of rotation marked out here. Now, let's say in this case, right, we have plate B which is fixed and plate A which is rotating with respect to plate B. Now, as you can see, if it's a rotation about this particular axis, right, so there will be a movement, and this movement, the angular velocity will be the same at all points along these plate boundaries. So along this, so all points along this plate boundary, the angular velocity is going to be the same. However, the linear velocity will actually vary, and this will vary according to the equation that we talked about. V is equal to omega r sine of theta. Now, what is this theta? Theta is this angle. The angle that is subtended by that particular point, right, with respect to the Euler at the center of the earth, with respect to the Euler axis of rotation. So this is the angular distance essentially. So this theta represents the angular distance of the point that we are concerned with respect to the Euler axis of rotation. So, and this is the angle that is subtended at the center of the earth. Now, as you can see, the further we are, right, angularly, the further we are from point P. So if the point was located at point P, theta would be equal to 0. So V would, the linear velocity would essentially be equal to 0. But as you move away along here, as the angular distance from the Euler pole of rotation increases, the value of sine theta increases, which means the value of sine theta increases, which means the value of V is equal to omega r sine theta also increases. R, by the way, is obviously, this is R, that's the radius of the earth. Okay, so this means then that the maximum linear velocity that we can expect, right, for anything that is following these principles is with respect to something that is oriented at 90 degrees with respect to the Euler pole of rotation. So it has to be present at an angle of 90 degrees with respect to the Euler pole of rotation here. Now, also the next thing that is of importance to us is actually remembering what the sign convention is. So what we do is we think of looking down. Suppose we were looking down this Euler axis of rotation, and if you remember, this is, I drew a beautiful eye here, right? So that's the eye. Let's darken it out a bit. So I'm looking down here. So if I'm looking down here, then if it is anti-clockwise, right, when I'm looking down along the axis from outside the earth towards the center of the earth, then if the rotation sense is anti-clockwise, right, if the rotation sense is anti-clockwise, then we say that that particular Euler axis of that particular pole of rotation is associated with a positive value. So it's the positive pole, and we call that P here, right? So it means this is the positive pole. Automatically it means that if we were actually looking down this part, right? So if we were looking down this part here, right, and that was my beautiful eye, and if I'm looking down here towards the center of the earth, obviously in this case it would be clockwise when I'm looking down from the center of the earth. So this particular Euler pole would then be a negative Euler pole. So this one would be the negative Euler pole. So you can have a positive Euler pole, you can have a negative Euler pole. So if one of them is a positive pole, the other one is the negative pole. So if you know the positive pole, automatically, of course, we know what the negative pole of rotation would be. So just to understand this, that the Euler pole of rotation, this is the sign convention that we are going to follow, right? And the sense of motion, what we are trying to get at is what would be the relative velocity, right, along a plate boundary if we are given certain values. Now, let's just think of what we are given and how we are going to proceed with it. Okay, now just a recap of what this actually means. Now, if you have, right, different Euler poles of rotation at different points on the earth, for example, India is actually moving in this manner with respect to, it's actually moving in this manner with respect to the Eurasian plate. So if I consider the Eurasian plate to be fixed, so if the Eurasian plate is fixed, India is actually rotating in this manner. Now the Euler pole of rotation for the Indian plate with respect to the Eurasian plate is roughly somewhere, I think it's roughly somewhere around here, let's say. So this would be the one for this is the Euler pole for India with respect to Eurasia. So forgive me for writing on the lettering that's there, but I think you can get the general drift of what I'm trying to follow. Now, what does this mean? So the velocity that you get at any point on this boundary, right, at any point on this boundary, would actually be proportional to its angular distance from this particular point with respect to the angular velocity here. And so the velocity would vary, the linear velocity along the plate boundary between India and Eurasia would vary accordingly. It would vary according to the angular distance from this Euler pole. So this would be the case for all other plate boundaries we know of. So every plate boundary, for example, for the India-Eurasia plate, I told you this is the Euler pole of rotation, and that would be the Euler pole of rotation for the Eurasian plate if we considered the Indian plate to be fixed, in which case, right, the velocities would have been like this. Okay, so that would have been just the opposite if we considered the Eurasian plate to be moving with respect to the Indian plate. Automatically then we must have, what this means is that every single pair of plates we have, say the South American and African plate, they must have an individual imaginary Euler pole of rotation, and associated to depict the movement along this particular plate boundary between them, we must also have some idea of what the angular velocity is along that imaginary Euler axis of rotation. So to point out or to pinpoint the orientation of the Euler pole of rotation for any pair of plates, right, any pair of plates, we need to have the value, the location of the Euler poles of rotation. Conventionally, we just depict it with the positive location of the positive pole, which means we can automatically find out the position of the negative pole. And also we need to specify the magnitude of the angular velocity. Because this is taking place on the surface of a sphere, the angular velocity associated with any pair of plate boundaries must be the same throughout that plate boundary. That will not vary. But what is important here is that the linear velocity will actually vary, and that is what we are able to measure, because when we are actually measuring any velocity along a plate boundary, that will be a linear velocity. So it is important for us to be able to be able to find out, to be able to characterize what the linear velocity is at any point along a plate boundary, because that will have a magnitude and also a direction, and that will give us some handle. That will also give us some handle on what kind of motion would exist along that segment of the plate boundary. So the problem of linear velocities varying along plate boundaries, this is something that we know of, and this is something that we will try to understand as we go on. So now let's try to understand exactly how we should be proceeding, right, in this particular case. And so we can just frame it as a problem, right? So let us say that there is a point x at any point along a plate boundary. So let x be any point on a plate boundary. So when we are talking about a plate boundary, we are talking about a specific plate boundary, and it can be between any two plates. So let's just imagine that x is a point on a plate boundary. Now, first of all, on the surface of the earth, the first thing we do is to point out what is north and what is south, right? We mark that out. Then let's say this point x that we are concerned with is, let us say, somewhere around here. So let's say this is my point x. Now likewise, just as I point out x, let P be the positive Euler pole of rotation. Let P be the positive Euler pole of rotation for this particular plate boundary. Let us say, let's just think of that Euler pole of rotation being this point here. Okay, so what we have, right, is we are given this, right, we have the positive Euler pole of rotation here, right, we have the point on which we have the the point that we are concerned with. So what we need to find out is what is actually the linear velocity, right, at this point on the plate boundary. Note that at this point I am not drawing the plate boundary. The plate boundary passes through x. It can have any orientation. It can pass this way, it can pass like this, it can pass this way. It doesn't matter. The important thing is that the linear velocity that we actually calculate at point x, because of an Euler pole of rotation at point P, will be the same. Its magnitude will be the same, its velocity will be, the direction will be the same. The azimuth of that velocity will also be the same. Because the angular velocity associated with this Euler pole of rotation, we will give it a value of omega. So let us assume that omega is the value that we are concerned with. This is the value that we all know. This is a value that is a magnitude that is given to us. Now let us also think, right? Let us also think that we have been given the values. Obviously, we need to be given the location of the Euler pole of rotation and the point x. So for point x, let us say the latitude and the longitude. Okay, let's just write it a little differently. So let's say the latitude and the longitude. Let's use the eraser. I'll cut out x here, and then I'll get back here, again do this, and say, let's say this is point x. Okay, so the latitude of point x, let us call it lambda subscript x, right? So the latitude, we will use the symbol lambda whenever we're talking about the latitude, and let the longitude be depicted by phi. So this would be phi x. So the position of point x on the surface of the earth is characterized, right? It's given by its latitude lambda x and the longitude phi x. Let us also say that we have given, right, we have to be given, in fact, the location of the positive Euler pole of rotation. So this point P, let us say that the latitude of this point P is lambda subscript P and the longitude is phi subscript P. So this is the longitude, right? We've been given the position of the longitude, right, of point P. So this is what we are given. The other thing, of course, that we have to be given, that we need to be given, right, is the value of omega, that is the angular velocity. So this is the angular velocity. So these are the things that are given to us, right? This is what we are given, we've been told. Now what do we have to find out? So x is any point on the plate boundary. So at this point on the plate boundary, what we need is to find out what is the value of the linear velocity v, right? So this is the linear velocity, right? And we also need to know its direction. This is the magnitude of the linear velocity, right? Let v be the magnitude of the linear velocity. And we also need its direction. Now what does this direction means? It means, you see, this one point x, the actual motion, the actual velocity could be like this, could be like this, could be this way, could be this way, right? So it will be a straight line. So all of these, the linear velocity at point x could be in any direction. Now how do we specify that direction? So the way that we will do it is we will specify the orientation of this line, right, direction of this line with respect to geographic north, right? So with respect to geographic north, and we'll say that that is the angular distance, the angle that it makes. So suppose this is the angle, suppose this is my actual velocity that we are going to be talking about, then in that case, right, so this, the angle that we are concerned with, right, would be the angle beta. So beta is the angular angle that we are going to use, right? This would be the angle that we are going to use to actually specify what is the orientation, right, which direction it is actually moving on the surface of the earth. So it would be an angle that we actually measure on the surface of the earth. So this is beta, is the azimuth of velocity measured on the Earth's surface. Okay, so this is what is given. So this, what is given to us as the angular velocity v, right? We're obviously given the radius of the earth r, we know that. We are given the latitudes and the longitudes of points x and y. These are the 2 points that actually concern us. So let's just now see how we can get about to this. So once again, on this rather large circle that I've drawn, so let's have geographic north, geographic south. Let's say this is point x, let us say this is point P. Okay. So now the values are the values that we had been given anyway before. Okay. Now the first thing to find out what the magnitude of what is the linear velocity at point x, which is any point on a plate boundary, what we think of is, first of all, we think of these, we join all these points which are on the surface of the sphere. So geographic north and point P, obviously this would be the arc of a circle like this. Similarly, we join geographic north and point x, which would be the arc of circle this way, and we also join points P and X also along the arc of a circle. So each of these, right, so this would go up to here, so just forgive my poor drawing. So we go up to here. So all of these are arcs, right? These are arcs of circles, right? These are each of these circles that I've drawn, these are actually great circles. So each of these, this is a great circle, this is a great circle, this is a great circle. So these are all arcs of great circles with respect to the earth. Okay. Now all of these, now we'll actually specify these in terms of the angles here. Now you see this angle here, this is on the surface of the earth, so it's actually the triangle NPX is a what we call a spherical triangle. Okay, angle NPX is actually a spherical triangle. So if it is a spherical triangle, right, we can actually, on the surface of a sphere, so it's a curved triangle. So this angle, which is the angle, it's a curved angle, right, on this spherical triangle, right. This, let us call this angle here, right, capital A. Similarly, this angle here, let us call it capital B. This angle here, let us call it capital C. So in other words, the spherical angle x n p, this is equal to A. The spherical angle n p x, this is equal to B, and the spherical angle n x p is equal to C. So this is the notation that we will now be using. So these are all spherical angles. Apart from this, right, there is one other thing that is important for us to know, important for us to use in this particular calculation. So that is the angular distance, right, along of NP, of XP and NX. Now what does this angular distance mean? Now the angular distance is the angle subtended by 2 points on a sphere at the center of that sphere. Now, if we use it in that sense, it means we join point N to the center of the earth, right? So we can actually think of it this way. So if you have this, so this is N. So let's say that is this point here. So if point P is out here, right? So if this is north south, then if I join P to the center of the earth here, this angle, right, is the angular distance. So this angle is this one. So NP now, the angular distance NP, let us now depict it by the symbol. We conventionally, what we do is we depict this angular distance by the small letter of the equivalent angle opposite on the spherical triangle. So NP in this triangle NPX, so side NP is opposite this angle here. So we will refer to this as small c. Similarly, let us say NX, right? NX, that is the angular distance of point X, right, with respect to geographic north, right? Let's call that is opposite. This point is opposite to the angle B, so we will call it small b. And this particular point XP, right, we will call this point XP, we will call this small a. So we have C, B and A, right, depicting these. Now, if we go on to this part here, so once again, when we are talking about north and south and we use these points, so a quick drawing. So my point X, as you notice, is shifting inadvertently, so don't pay much attention to that. So that's A, right? So this was my B, this was C, this was small c, this is small b, and this is small a. Okay, so now with respect to this, now what we need to do is, what is important for us to find out is that when I'm trying to find out the linear velocity of point X with respect to point P, right, what it actually means is that if I draw a triangle circle like this, right, and this was point P and this is point X, right, sorry, so then if this was point X, then what I need is, right, this particular angular distance A, that is what is important to me, because the linear velocity V here would be equal to omega, which is given to us, into r, which is the radius of the earth, into the sine of this angle A, right. So the angular distance between point P and X, that is small a, that is what I'm interested in. So this would be small a, this angular distance. I need to find that out. However, I don't know what that value is. The question is, can I find it out from the other values that are given to me? Well, it turns out that we can actually simplify matters a bit. Let's go about it this way. Let's look at small b. Small b is this particular arc. What is small b? Now, small b itself, right, that if we look at it, is equal to, it is actually the angular distance subtended by point X at the surface of the earth with respect to the geographic north pole. However, the latitude of this particular point, so suppose now this particular point is point X, now suppose that was point N, then in that case, right, this angle in this case would actually be the latitude of X. So let's cut this out. So this angle here would be the latitude of X. So in other words, this angle, this is the equatorial plane, right? So in this case, this angle here, this angle that we are concerned with, the angular distance from the north pole, would be 90 minus the latitude. So b, the small b, becomes equal to 90 minus lambda of X. By an absolutely similar logic, small c, which is the angular distance of P with respect to the center of the earth, right? So that would actually be equal to 90 minus lambda p. So we actually know, because we have been given the values of lambda p and lambda x. So we know what this is. Now another value that we actually need is this value of capital A. That is also something that we know. How do we know this? Now imagine what this is. What ultimately, this is the angle on the spherical surface of the earth, right? But what is NP? NP is a segment of the longitude that passes through point P. Similarly, NX is a segment of the longitude that passes through point X. Now, we have been given the longitude of point P. We have been given the longitude of point X. So, in other words, we've been given capital A. So, we can actually say that the angular distance A is equal to phi of P minus phi of X, because this is the phi of, this longitude is phi P, this longitude is phi X, and therefore A is equal to phi P minus phi X. Okay. Now, to actually resolve this now, the next thing that we do is to use the cosine rule for spherical triangles. We use the cosine rule for spherical triangles. Now this actually can be stated in this way: cos of A is equal to cos of B cos of C plus sine of B into sine of C into cos of capital A, right? So this is the cosine rule for spherical triangles. Just as we have sine and cosine rules for normal triangles, we can have sine and cosine rules for spherical triangles. Now in this particular case we can rewrite it, because cos of A would also be equal to, now cos of B is equal to 90 minus lambda x. Therefore cos of B can be rewritten as sine of B. Similarly, cos of C can be rewritten as sine of C, right? Plus sine of B would therefore become cos of B. Sine of C would become equal to cos of C, and cos of A, capital A, would simply become equal to cos of phi p minus phi x, right? And this A, which is something that we wanted to find out, would be equal to the cos inverse, right, of this value. So it would be the cos inverse of sine B sine C plus cos B cos C cos of phi p minus phi x. Okay, so we've actually found out the value of small a. So this means then that since we know the value of small a, we've been given the value of omega, the magnitude of the linear velocity is something that we now know. We can actually calculate that. So what about the next step then? We know the magnitude of the linear, the angular velocity, the magnitude of the angular velocity. So once again, this is x and this is p, this is n, this is s, right? So how do we now actually specify what the velocity would be here? Now we know the magnitude is small v, but how do we know what its orientation is? Now we know, you see, if this is the case, if this is the positive p, right? So let's say this is point P. So I'm depicting this, I'm cutting a slice through here, and this is my point X. Then with respect to point P, right, if point P is a positive pole of rotation, then point X will actually be moving away tangentially, right, from this boundary, because it will be moving along a small circle. So if I consider a small circle like this passing through X, so it will be moving along a small circle, right, and because this is a positive pole of rotation, right, it would be moving in a particular manner with respect to this. So in this case, because it's positive, it should be moving with this value here. Now what is this actual value exactly? How much does this value actually come to? We know that this must be this part, because it has to be tangential with respect to the longitude, right? It has to be tangential with respect to the longitude. You see what I mean is that if you had a line of longitude like there and the point X was here, then point X would move along a small circle, and this would be at right angles to this particular line of longitude. So with respect to the arc Px, which is a line of longitude with respect to the Euler pole of rotation P here, then this must be equal to 90 degrees, this line here, and this angle is C. So this vector here, right, would simply be, the direction must be equal to 90 plus capital C. But how do we find out capital C here? This is something we don't know. C is equal to what? We can then, to find out C, we can use the sine rule for spherical triangles. And the sine rule for spherical triangles, you can write it as sine of small a divided by the sine of capital A is equal to sine of small c divided by sine of capital C. Now we know all the others, therefore C must be equal to, capital C must be equal to sine inverse, right? It must be the sine inverse, right? If we put in the right parts, it would be the sine inverse of the cos of lambda p into the sine of phi p minus phi x, right, divided by the sine of small a, which we just determined. So now you can actually see that we've actually can find out exactly what this value would be. So the value of beta would be equal to 90 plus c. So this would be the whole value of beta. This is what we would get. Now the value of c that we had get here, the sine inverse, remember that it could be double valued. So this double value, both of these would are possible. So it's important for us to be able to specify which one it is. So this is where you have to intuitively work out exactly what that velocity would be, right? How would you actually make sure that you've got the correct sine value when you're actually inverting for the sine inverse. So this way then, what it means is that we can actually calculate both the magnitude of the linear velocity as well as its direction at any point along a plate boundary, given the location of the Euler pole of rotation, given obviously the location of the point concerned, and of course the angular velocity concerned with that particular plate boundary. So to conclude this particular session, right, what we can say is that the linear velocity and its azimuth at any point, azimuth means the direction, at any point on a plate boundary can be calculated given the location of the Euler poles of rotation and also the angular velocity associated with the pair of plates concerned. So this is something that we can calculate. So once we given this value, that means that we have enough information to be able to calculate anything for any pair of plates that we are concerned with. So we use the same two references that we've used so far, and thank you till the next class.